Hello, my dear. I'm glad to see you again. And let's start our lecture number 10 on avionics engineering course. Okay. Uh, Today's topic is navigation system. I hope this is very, very interesting topic. Okay. So let's start with first question of this lecture. It's called Introduction and Basic Principles. You know, the dictionary definition of navigation is a good one. So, navigation, the act, scientific, or art of directing the movement of a ship or aircraft. Navigation thus involves both control of the aircraft flight path and the guidance of its mission. The measurement of the aircraft attitude with respect to the horizontal plane in terms of the pitch and bend angle and its heading, that is the direction in which it is pointing in the horizontal plane with respect to the north, first of all, okay? And this is essential for both control and guidance. This information is vital for the pilot to fly the aircraft safely in all weather conditions, including those when the normal visibility of the horizon and landmark is poor or not available. For example, in haze or fog conditions, flying in cloud and night flight, attitude and heading information are also essential for the key avionics systems which enable the crew to carry out the aircraft mission. These systems include the autopilot system, like attitude and heading hold mode, auto land, etc. Navigation system and weapon aiming system. The information is also required for pointing radar beams and infrared sensors. Accurate knowledge of the aircraft position in terms of its latitude or longitude coordinates, ground speed and track angle, high and vertical velocity is also equally essential for the navigation of the aircraft. The need for accurate and high integrity navigation is briefly summarized, will be summarized in our lecture. Okay? So, for civil aircraft, the density of air traffic or on major air routes requires the aircraft to fly in a specified corridor or tube in the sky. These air routes being defined by the Air Traffic Control Authority. Not only must the aircraft follow the defined three-dimensional flight path with the high accuracy, but there is also a fourth dimension, namely that of time, as the aircraft arrival time must correspond to a specified time slot. Are you agree with me? Nice. High accuracy navigation systems are thus essential and form a key part of the flight management system. For military operations, very accurate navigation systems are essential to enable the aircraft to fly low and take advantage of terrain screening from enemy radar to avoid known defenses and, in particular, to enable the target to be acquired in time. The aircraft flies fast and very low so that the pilot cannot see the target until the aircraft is very near to it. There may be then only about 6 to 10 seconds in which to acquire the target, aim and launch the weapon. It is thus necessary to know the aircraft's position near the target area to be seen 100 meters accuracy. And this enables the target sight line to be continually computed, like knowing the target coordinate, including target height and the aircraft height, and a target maker symbol to be displayed on the HUD. And this should be near the target, and the pilot then slews the maker symbol to exact overlay the target. And this corrects the error and initiatives the weapon aiming process. The use of standoff weapons, which are released several kilometers away from the target, also requires an accurate knowledge of the aircraft's position in order to initialize the mid-course inertial guidance system of the missile. It means like the terminal homing phase is achieved with a suitable infrared or microwave radar seeker. Clearly, the integrity of the navigation system must be very high in both civil and military aircraft, as large navigation error could jeopardize the safety of the aircraft. And there are two basic methods of navigation, namely dead reckoning or DR navigation and position fixing navigation system. Both systems are used to achieve the necessary integrity. As briefly explained in first lecture, dead reckoning navigation is the process of continually computing a vehicle's position as the journey proceeds from a knowledge of the starting point position and the vehicle's speed and direction of motion and the time elapsed. It is essentially an incremental process of continually estimating the changes that have occurred and updating the present position estimate accordingly. The main types of airborne DR, dead reckoning navigation systems, are categorized below on the basis of the means used to derive the velocity components of the aircraft. In order to increase accuracy, these are, first of all, air data-based DR navigation. The basic information used comprises the true airspeed from the air data computer, with wind speed and direction like forecast or estimate, and the aircraft heading from the attitude heading reference system, AHRS. Second, Doppler or heading reference system. These use a Doppler radar velocity sensor system to measure the aircraft's ground speed and drift angle. The aircraft heading is provided by an attitude heading reference system. Third, inertial navigation system. This derives the aircraft velocity component by integrating the horizontal component of the aircraft acceleration with respect to time. These components are computed from the outputs of very high accuracy gyroscope and certainly accelerometers, which measure the aircraft angular and linear motion. And fourth, Doppler inertial navigation system. This combines the Doppler and INS output generated by means of a Kalman filter to achieve increased DR navigation accuracy. The primary DR navigation system, which is also the primary source of very accurate attitude and heading information, is the inertial navigation system for INS. The third inertial reference system, IRS, is also used in civil aircraft. The IRS can have a lower inertial navigation accuracy of up to 4 miles per hour error, compared with 1 to 2 miles per hour for typical INS. The attitude and heading accuracy, however, is still very high. The terminology INS or IRS is used in our lecture to show they are essentially the same. Okay? Nice. So, the fundamental feature of INS or IRS systems is that they are the Schule-tuned systems. This is achieved by precise feedback of the components of the aircraft velocity in the local level plane, and so that the system tracks the local vertical as the aircraft moves over the Earth's surface. Schule tuning requires very accurate gyro and accelerometers and precise computing. The payoff, however, is that it enables a very accurate vertical reference, like fraction of a minute of arc error. It's all to be derived, which is independent in the aircraft acceleration. A very accurate heading reference is established in the pre-take or initial alignment phase using gyro compassing. The very large gyro drift rate, like less than 0.01 degree per hour drift uncertainty. All this enables an accurate heading reference to be maintained for several hours. The INS or IRS also derives the aircraft velocity vector in conjunction with the air data system, which provides barometric high information. This is of great assistance of the pilot when displayed on the HUD. I hope you remember. It was accented on lecture number 2. Accurate velocity vector information is also essential for the aiming of the unguided weapon, like guns, bombs, and rockets in military aircraft. The step-down configuration of the gyros and accelerometers, which is now used in modern systems, enables the INS or IRS to provide body angular rate and linear acceleration components for the flight control system. The INS or IRS is thus a key aircraft state sensor for both military and civil aircraft. Large civil airliners operating on long-haul over water routes and have triple IRS installations to ensure availability and the ability to detect failures or degradation of performance by cross-comparison. They are also a key sensor for the automatic flight control system. Smaller short-haul civil airlines are now generally equipped with a dual IRS installation with 2.5 or 4 miles per hour navigation accuracy. Lower accuracy systems cost less. The flight time is shorter, and they operate over routes which are well covered by ground-based radio navigation aids. They are also equipped with a GPS, which can be used to correct the IRS through a common system. A number of manufacturers now provide a combined air data system and inertial reference system as a single unit known as an air data inertial reference system. This has a number of advantages, such as lower cost, lower weight, and occupies less space. Only one box is required, and the power supply conditioning electronic, computer, and most of the interfacing electronics can be shared by the two functions. Barometric high information is also essential for the vertical inertial check. Attitude heating reference systems are lower accuracy than the INS or IRS, and generally provide a secondary source of attitude and heating information. They use less accurate but lower cost gyros and accelerometers, which are insufficiently accurate for Schuler tuning to be effective. Long-term air data velocity mixing is used to constrain the vertical error, and long-term magnetic monitoring from a magnetic heating reference is used to constrain the heating error. In general, these systems are an order of magnitude, or even more, less accurate than our famous INS or IRS. And they are, however, of considerably lower cost than INS or IRS systems, and the stripped-down configuration adopted together with the use of solid-state gyros and accelerometers ensures they have very high reliability. They provide the primary source of attitude and heating in some aircraft, such as helicopters and smaller civil aircraft. The heating information from the AIRS is used for air database DR navigation, generally a reversionary mode. And in the Doppler-based DR navigation systems, which are installed in many helicopters today. It should be noted that also Doppler radar velocity sensors are widely installed in helicopters. They are no longer fitted in the new generation of military helicopters and strike fighters. This is because the radar energy emission from the Doppler increase the risks of detection. That is the name of the game. And civil aircraft used to have Doppler, but these were superseded in the early 1970s with the introduction of civil IM systems. A fundamental characteristic of dead recording navigation system is that the accuracy is time-dependent. For example, a good quality INS has an accuracy of 1 mile per hour, so that the aircraft position uncertainty after 5 hours would be 5 nautical miles. A position fixing system is thus required to constrain the error caused of a dead reckoning navigation system and correct with a DR position error. A position fix can be obtained by recognizing a prominent landmark or set of terrain features either visually, possibly using an infrared imaging sensor, or from radar-generated map display. Alternatively, a suitable position fixing navigation system can be used. In general, several dissimilar systems may be used to provide the necessary confidence in the overall navigation accuracy. Position fixing navigation systems depend on external references to derive the aircraft's position. For example, a radio or radar transmitter on the ground or in satellite whose orbital positions are precisely known. Unlike data recording navigation systems, the errors are not time-dependent. The errors are also independent of aircraft position in most position-fixing systems. The main position-fixing navigation systems in current use are briefly summarized just now. So, first, range and peering radio navigation aid. This comprises VOR or DME and TACAM. VOR, it means VHF omnidirectional range, is an internationally designed short-distance radio navigation aid and is an integral part of air traffic control procedure. DME, distance measuring equipment, is co-located with VOR and provides the distance from the aircraft to the DME transmitter. TACAM is a primarily tactical air navigation system for the military services of the USA and NATO countries. It is often so-called with civil VOR stations. Such combined facilities being known as VOR TAC stations. The system are line of sight systems and provides the slant range of the aircraft from the ground station using a transmitter or transponder technique. A rotating antenna system at the TACAN ground station or beacon enables the aircraft to measure the peering of the TACAN beacon to an accuracy of about 2 degrees, using a principle analogous to a lighthouse. Navigation position accuracy of VOR or DME and TACAN is of the order of 1 to 2 miles. There used to be other radio navigation systems in operation, which use a chain of ground-based transmitting stations. The systems use pulse transmissions and operated by measuring the phase differences between the signals received from the different transmitter stations. They are referred to as hyperbolic radio navigation systems. These systems have been progressively discontinued over the years. Omega was discontinued about 2000 millennium. And the last remaining system, Lorentz C, was very recently discontinued in 10 years later, in February 2010. The system goes back to the GEE system developed by the UK during the Second World War, and which entered operational service with the RAF in 1942. It was effective, a dramatic improvement in navigation accuracy at a critical time. They are all now of historical interest only and will not be discussed further. Okay? And now let's start with satellite navigation system, GPS. GPS or global position system. GPS is the most important and accurate position fixing system developed today. It is being used by every type of vehicle, aircraft, ships, and land vehicles too. Civilian use is now very widespread. For example, GPS receivers are fitted in very many cars, vans, and lorries, and they are readily affordable for ramp. The equipment required by the GPS user is entirely passive and requires a GPS receiver only. Electronic miniaturization has enabled very compact and lightweight GPS receivers to be produced. The full positional accuracy of 16 meters in 3D and velocity accuracy of 0.1 meter per second is now available to civil users. Previously, only military users were able to achieve this accuracy. Precise time to within a few billionths of a second is also available. The use of GPS in conjunction with a ground station system, which transmits correction to the user system, known as differential GPS, has enabled a positional accuracy of 1 meter to be achieved. Construction of an independent European system known as the Galileo satellite navigation system is begun and is scheduled to come into operation around 2014. The system will be in nearest years interoperable with GPS and with 40 orbiting satellites, and will provide an accuracy worldwide of the order of 1 meter. Terrain Reference Navigation System, TRN. Terrain Reference Navigation System derives the velocity's position by correlating the terrain measurement made by a sensor in the vehicle with the known terrain feature data in the vicinity of the TR estimated position. The terrain feature data is obtained from a stored digital map database. Figure on this slide shows the information flow from the inertial sensor systems, air data system, and the position fixing radio navigation system to the user system. The accuracy of the INS or IRS can be greatly improved by combining the inertially derived position data with that from a position fiction navigation software, such as GPS. This is achieved by using a statistical predicting filter known as a Kalman filter, which provides an optimum combination of the two sources of data. The resulting combination is superior to either source on its own and retains the best features of each system. Let's start from basic navigation definition. A very brief review of the terms and quantities used in navigation is set out for this one. Position on the Earth's surface is generally specified in terms of latitude and longitude coordinates, which provide a circular grid over the surface of the Earth. The Earth is basically a sphere. I hope you remember. The variation in the radius of the Earth is only about 40 nautical miles in a radius of 3,438 nautical miles at the equator, being slightly flattened at the pole. This variation is considered in the navigation computation. Referring to the figure on this slide, latitude and longitude are defined with respect to the polar axis, the equator, and the prime meridian. A meridian is a circle around the Earth passing through the north to south pole. The prime meridian is the meridian passing through the Greenwich, and see if this measured here, Greenwich, which provides a datum for measuring the longitude. The latitude of a point on the Earth's surface is the angle subtended at the Earth's center by the arc along the meridian passing through the point and measured from the equator to the point. I hope you see all of that, right? The range of latitude angles is from 0 to 90 north and 0 to 90 to the south. The longitude of a point on the Earth's surface is the angle subtended at the Earth's center by the arc along the equator measured east or west of the prime meridian to the meridian passing through the point. The range of longitude angle to cover all points on the Earth's surface is thus 0 to 180 east of the prime meridian and 0 to 880 degrees west of the prime meridian. Very logical, right? The latitude and longitude are expressed in degrees, minutes of arc, and seconds of arc. Great circles are circles on the surface of a sphere, which with their center at the center of the sphere. And that is the plane of a great circle passes through the Earth's center. Meridians and the equator are thus great circles. Parallels of latitude, which are circles around the Earth parallel to the equator, and are, however, small circles. The shortest distance between 2 points on the surface of a sphere is a great circle, and hence navigation routes try to follow a great circle path. Navigation between points on the Earth's surface thus involves the solution of spherical triangle as shown in this slide. A spherical triangle being defined as a triangle on a sphere whose sides are part of great circle. The solution is achieved using the well-established formula of a spherical trigonometry. Basic dead recording navigation system. The basic principles of deriving a DR navigation position estimate are explained for this moment. The following quantities are required. First of all, initial position, latitude or longitude. Second, the northerly and easterly velocity component of the aircraft, V sub N and V sub E. Referring to this figure, it can be seen as the rate of a change of latitude here. For rate of a change is longitude mu dot. So mu dot will be proportional V sub E over R radius, right? Times second of 1. The change in latitude over time is thus equal to 1 over R, an integral from 0 to time from V sub N dt, and hence the present latitude at time t can be computed given the initial latitude lambda naught. So, similarly, the change in longitude is equal over 1 over R integral from 0 to t v sub e is second lambda dt, and hence the present longitude can be computed given the initial longitude mu naught. So we may transcribe this for lambda and mu equation. It can be seen that a mathematical singularity is approached as lambda approaches 90 degrees, and seconds for lambda approaches infinity. And this method of computing the latitude and longitude of the dr position is hence limited to latitudes below 80 degrees. A different coordinate reference system is used to deal with high latitude, as will be explained a bit later. Okay? So, the basic computational processes in a dr navigation system using a Doppler or hidden reference system is shown in this slide. In the case of a Doppler or hidden reference system, the ground speed v sub g and drift angles delta are measured directly by the Doppler radar velocity sensor system. The HRS system provides an accurate measurement of the hidden angle psi, and hence the track angle psi sub t, track angle, and can be obtained from this simple form. The northerly velocity component of the aircraft v sub n and the eastern velocity component v sub e are then derived by resolution for the ground speed vector. Ground speed vector v sub g. Okay? So, hence, v sub n will be proportional v sub g cosine psi t, and v sub e, or to east direction, proportional v sub g to sine psi t. In the case of an air data-based dr navigation system, the northerly and easterly velocity components v sub n and v sub e of the aircraft can be derived as follows. First of all, the horizontal velocity component v sub h of the true air speed v sub t is obtained by the resolving v sub t true air speed through the aircraft pitch angle theta. So we may write v sub h proportional v sub t times cosine theta. Second, the northerly and easterly velocity components of the airspeed are then derived by resolving v sub h, the horizontal velocity component, v sub h, through the aircraft hidden angle psi. So we may write as a northerly airspeed proportional horizontal velocity component times cosine psi hidden angle, and easterly airspeed proportional horizontal velocity component v sub h times sine from psi hidden angle. So next, the forecast or estimate wind speed v sub w and the direction psi sub w is resolved into its northerly and easterly component. So the northerly component proportional v wind speed times cosine psi w, and eastern components will be proportional wind speed times sine instead of cosine, sine psi w. Next, the northerly and easterly velocity components of the aircraft are then given by these two equations. So the nozzle velocity components proportional V sub I cosine psi plus V sub W wind speed cosine psi W. And easterly wind components proportional V sub I times sine psi and plus wind speed V sub W times sine from the psi double. So such a system provides a reversionary dead recalling navigation system in the absence of Doppler or an INS and would generally be used in conjunction with a radio navigation system. And now time to start with very interesting topic, inertial navigation. It is instructive to briefly review the reasons for the development of inertial navigation and its importance as an aircraft state system. The attributes of an ideal navigation and guidance system for military applications can be summarized as follows. First of all, high accuracy, self-contained, autonomous, it means does not depend on the other system. Passive means does not radiate, unjammable, and does not require a reference to the ground or outside world. In the late 1940s, these attributes constitute a wish list and indicated the development of inertial navigation as the only system which could be capable of meeting all these requirements. It was thus initially developed in the early 1950s for the navigation and guidance of a ballistic missile, strategic bomber, ships, and submarines, like ships' inertial navigation systems, SINS. Huge research and development programs have been carried out worldwide involving many billions of dollars expenditure to achieve viable systems. For instance, as mentioned earlier, over 3 orders of magnitude improvement in gyro performance from 15 degrees per hour to 0.01 degree per hour drift uncertainty was required. House comparison? Precision accelerometer had to be developed with bias uncertainties of less than 50 milli G. And the major task of achieving the required computational accuracies had to be solved, and in fact, the first digital computers operating in real time were developed for IM systems. Once these problems had been solved, however, the INS can provide accurate position in whatever coordinate is required, like latitude or longitude, ground speed and track angle, Euler angle, heading, pitch, and roll to very high accuracy. Aircraft velocity vector in conjunction with the air data system. Accuracy velocity vector information together with an accurate vertical reference are essential for accurate weapon aiming, and this has led to the INF being installed in military strike aircraft from the early 1960s. On board as a key element of the navigation and weapon aiming system. The self-contained characteristic of an inertial navigation system, plus the ability to provide a very accurate attitude and heading reference led to the installation of IM systems in long-range civil transport aircraft from the late 1960s. They are now very widely used in all types of civil aircraft. A good question to ask an interviewee who is interested in entering the avionics system field is, how can you measure the motion of a vehicle and derive the distance it has traveled without any reference to the outside world? The answer is that you can sense the vehicle's acceleration and also the gravitational vector of its accelerometer, right? If the vehicle's accelerations component can then be derived along a precisely known set of axes, successive integration of the acceleration components with respect to time will yield the velocities and distance traveled along these axes. This is true provided the initial conditions are known, and that is the velocity, the vehicle velocity and position at the start time. And figure on this slide illustrates the basic concepts of deriving the velocity and distance traveled of the vehicle from its acceleration component. Put like this seems simple. Any error, however, in the deriving the aircraft acceleration component from the accelerometer output will be integrated with time, producing velocity error, which in turn are integrated with time-generated position error. For example, a constant accelerometer bias error P capital here, P capital, which can be equated to an initial tilt error. And all of this will result in a distance error, which is equal for a double integral from b dt to time. That is bt squared over 2 as a result. The resulting distance error is thus proportional to the square of the elapsed time. An accelerometer bias error of 10 in power minus 3g will produce a distance error nearly 0.45 kilometers after 5 minutes and 1.m kilometers after 10 minutes, for example. Error is deriving the orientation of the accelerometer input axis with respect to the local vertical, that is tilt error, and introduce gravitational acceleration errors in the acceleration measurement. Refer to figure on this slide. A tilt error, namely delta theta tilt error, produces a gravitational error equal g times delta theta. Delta theta is a very, very small error. Okay? A constant gyro drift rate W capital will cause the tilt error delta theta to increase linearly with time. So what it means, delta theta in this case will be proportional W times t, resulting in a gravitational acceleration error GWT. And this results in a distance error by means of this next integral, yes? And that gets us that G times W times T cubed over 6. The distance error in this case is proportional to the cube of the time. And we can see this from the last expression, right? For example, a gyro drift rate of 1 degree per hour results in a proportional error of 0.2 kilometers after 5 minutes and 1.6 kilometers after 10 minutes. So, a relatively large sensor error are used in the above example to show the importance of sensor accuracy. Clearly, these types of error propagation are unacceptable, except in applications where the time of flight is short, like mid-course guidance of short-range missions, or where the system could be frequently corrected by another navigation system. But it should be noted that these error propagations approximately closely to the initial error propagation with Schuler tuning over the first few minutes. This is because the correction action exerted by Schuler tuning of the tilt errors take place over an 84.4 minutes period, and so is small over the first few minutes. It will be shown that Schuler tuning provides an undamped closed-loop correction action to constrain the system tilt error, and so that they oscillate about a zero value with an 84.4 minutes period. The INS vertical follows the local vertical irrespective to the vehicle acceleration, and so that the system behaves like a Schuler pendulum. Schuler tuning completely changes the error propagation characteristics from those just described and enables a viable unaided navigation system to be achieved. It is a vital and fundamental integrated of any IN system. The concept of a pendulum, which would be unaffected by acceleration and would always define the local vertical, was originated by the Australian physicist Max Schuler in 1924. These authors from studies he carried out on the error in marine gyro compasses resulting from ship maneuvers and the effect of ship acceleration on the pendulum gyro compasses. Schuler conceived the idea of a pendulum which would be unaffected by acceleration by considering the behavior of a simple pendulum whose length was equal to the radius of the Earth, as you can see on this slide. The plumb bob of such a pendulum would always be at the Earth's center and would hence define the local vertical irrespective of the motion, right? Or acceleration of the point of suspension of the pendulum. It means any disturbance to the pendulum bob would cause it to oscillate about the local vertical with a period proportional to pi and square root from r over g. Here r is the radius of the Earth and g is the gravitational acceleration. Using the accepted value for radius and g gives the period of the Earth's radius pendulum or Schuler pendulum that scatters 84.4 minutes. A simple pendulum of length equal to the Earth's radius is obviously not feasible, right? If, however, a pendulum system could be produced with an exact period of this 84.4 minutes, then it would indicate the local vertical irrespective of the acceleration of the vehicle carrying it. In 1924, the technology was not available to implement a practical system. And in fact, it was not until the early 1950s that the technology became available to implement a practical Schuler-tuned IN system. first successful airborne demonstration of a Schule-tuned inertial navigation system was achieved by Dr. Charles Stark Trapper and his team in Massachusetts Institute of Technology, MIT, at Boston in USA, around 1952. The basic principles of any IM system are to derive the components of the aircraft acceleration along local level axes, generally the north and east axis, using an orthogonal set of accelerometers and gyros to measure the aircraft motion. Integration with respect to time of this acceleration component then gives the aircraft's north and east velocity component, knowing the initial condition. The aircraft position in terms of its latitude and longitude coordinates can then be derived. As already explained, it is essential that the system is Schule-tuned to bound the tilt angle error in deriving the local level plane. The Schule-tuned stable platform was the only viable way of accurately deriving the north and east components of the aircraft acceleration from the early 1950s to the late 1970s, so nearly 20 years. And this is because of limitations in angular momentum gyro technology. Ring laser gyro of inertial accuracy achieved production status in the late 1970s and enabled a strap-down IM system to be implemented. As explained a bit earlier, RLG, based on strap-down IM systems, have suspected the stable platform-based system. The implementation of a Schule-tuned strap-down INF and a stable platform INF are mathematically identical. The Schule-tuned strap-down INF can thus best be explained and visualized by considering the system to have a mathematical model of a stable platform. That is a virtual stable platform within the system computer. And figure on this slide is a block diagram of a Schule-tuned strap-down IM system. The virtual accelerometer output are derived from the body-mounted accelerometer output by the axis transformation processes explained in our last lecture. Their outputs are the same as the real accelerometers would have when mounting on a real stable platform. The north and east accelerometers output, however, are sensed along the north, east, down. We have a three N, E, and D, N, E, and G letters, capital letters. Okay? N, E, N, E, and D letters. Axis, yes, three components. Axis, which are rotating slowly in space with the Earth's rotation. This axis rotation introduced Coriolis acceleration component. As explained, will be explained a bit later during our module. The aircraft also experiences small centrifugal acceleration components as it follows the Earth's curvature. Are you agree with me? Okay, nice. The Coriolis and centrifugal acceleration components are small, less than 0.05 meters per second, per square second, but nevertheless need to be computed. And the real, or correct say, virtual accelerometer output, correct before integrating with respect to time to obtain the aircraft north and east velocity component. The virtual prop is very accurately aligned with the local N, NEG axis, local NEG axis, during the initial alignment and gyrocompassive phase. Thereafter, it is rotated at the approximate Earth rotation rate component and the appropriate vehicle rate component so as to maintain alignment with the local NEG axis. The vehicle rate components are derived by integrating the corrected north and east accelerometer outputs with respect to time. And this inertially derived vehicle rate feedback provides the Schuller pendulum characteristic. The local value of the Earth radius, R capital, is used together with the local value of the gravitational constant G to achieve accurate Schuller tuning. I hope you remember the Schuller period is 2 pi times square root from R over G, right? And in this figure is basically like figure on previous slide. Are you agree with me? Basically, yes. And is intended to aid visualization of the process of tracking the local vertical as the aircraft moves over the Earth surface and the Schuller pendulum characteristic. Errors in the derivation of the vehicle rate term will result in the platform tilting from the horizontal. And these errors result from two main components. First of all, accelerometer bias error, which result in bias error, B sub N and B sub E, in the north and east acceleration components derived from the Thread town accelerometer. And second result from gyro drift rate, which introduce a direct error in the applied vehicle rate about the north and east axis of W sub N and W sub E, and have a major effect on the system accuracy, as will be explained here. These errors, in turn, produce tilt angle error. It will be delta theta N and delta theta E about the north and east axis, right? These introduce gravitational acceleration components. It must be multiplying here G times delta theta E and G times delta theta M along the east and north axis, and given by these two expressions. These two expressions for delta VE and delta VM. This velocity error results in vehicle rate error, delta VE over R, delta VE over R, and delta VN over R about the north and east axis, right? The sense of the vehicle rate error in the Schuller loop is such as to slow down or speed up the applied vehicle rate to try to restore our delta theta N and delta theta E. Restore is to zero. In fact, due to the two integrations taking place in the loop, the system will oscillate about the local vertical, as will be shown mathematically. A physical non-mathematical explanation of the Schuller loop is given at the end of this module. The rate of tilt about the north axis is equal to the delta VE over R plus W sub M. And hence, we can get these expressions for delta theta N dot will be negative value 1 over r and integral from this part. The minus sign is from the delta v e over r term is because of feedback is negative. Okay, and hence we have the delta for theta sub m, not dot, yes, next integration. So minus 1 over r and double integral. And differential twice and rearranging this, get us these expressions. Very nice and complete. A similar equation for delta theta e can be obtained with the forcing functions being p sub m and w sub p. I hope you will be very simple to get by your own hand. Okay? Now, it is convenient to drop the suffixes m and e in the above equation so that the solution can be applied to either axis. Solution in this form: d capital squared plus g over r as one component, yes, in parentheses, times delta theta equal p over r plus g w hat. The local vertical closed loop tracking system produced by Schuler tuning is shown in this block diagram and provides an error propagation model of an I and F. The effects of accelerometer bias and gyro drift are considered separately for the sake of simplicity. The effects of the system of a combination of disturbing input of accelerometer bias and gyro drift can then be inferred. And let's look for beginning effect of accelerometer bias. In this case, assume W equals 0. So the accelerometer bias can be equated to an initial TIL and will be proportional V over G in radian. The solution of our equation for initial condition here, delta theta from 0 initial, will be simply B over G, and delta theta dot from 0 will be the same 0. And that gets us very simple expression. Delta theta will be proportional V over G times cosine omega naught times T. Omega naught here is the square root from G over R. This is undamped nature of frequency over Schuler loop. The platform thus oscillates about the local vertical with amplitude over the B over G, and the period is 2 pi times square root from RG. That gets us our, we know that value is 84.4 millimeters. The acceleration error is G, acceleration error G times delta theta. The velocity error is integral from B cosine omega naught T to D. And the distance error is double integral from the same value. Okay? And hence, we can get the distance error proportional to B over omega naught square E times the component in parentheses, 1 minus cosine omega naught T. Figure on the right side shows the effect of an accelerometer bias error equivalent to an initial TIL of 1/2 minute of R. That gets us as 1.45 times 10 in power minus 4G. And this result is an oscillatory error between 0 and and 1 nautical mile. Next slide will be show us effect of gyro drift. In this case, assume that B equals 0 and gyro drift rate W will be constant. The solution of our equation for initial condition will be next one. Delta theta from 0 will be 0, and delta theta dot from 0 must be as double. In this case, delta theta will be proportional W over omega naught times sine omega naught t. Thus, the platform oscillates about the vertical as before with 84.4 minutes per year, right? This is logical. A gyro drift rate of 0.01 degree per hour results in a very small amplitude oscillation about the vertical of 0.14 minutes of hour. In this case, the velocity will be transformed as integral from GW over omega naught times sine omega naught t dt that get us W times radius and component 1 minus cosine omega naught t. The velocity error thus oscillates between 0 and 2W times r. And the distance error will be expressed by this expression integral from VW. Second component is parentheses, identical as before, right? And over dt and get us VWR and in parentheses t minus 1 omega naught times sine omega naught t. The distance error is thus proportional to the time of flight. The small amplitude oscillatory component being swapped after a while. A constant gyro drift rate of 0.01 degree per hour that get us 0.6 minutes of r per hour will be given average velocity error of 0.6 kilonewtons. That is a distance error, which is built up at a rate of 0.6 miles per hour. But it should be noted that this represents the error built up along the north and east axis, so that the radial error will be multiplied by square root from 2, and hence will be equal to 1 nautical mile per hour. And this figure on the right side illustrates the errors growth for a constant gyro drift of 0.1 degrees per hour. In practice, this is not a constant quantity, and the distance error over a long period is proportional to the square root of the time of flight, if the variation in the gyro drift is random. The very accurate vertical reference provided by Schuler tuning can be seen even a gyro drift as high of 0.25 degrees per hour results in a peak vertical error of 3.5 minutes of r. A physical explanation of a Schuler tuning is set out below for this now, as it is important to have a physical appreciation as well as a mathematical understanding. Referring to this figure on this slide, suppose the platform is being rotated at the same rate as the local vertical, but is tilted downward, right? From the local vertical by a small angle, like we have this tilted delta theta. At moment when t equals 0, the platform tilt results in the accelerometer measuring a small negative component, as we can see in this left figure, of the gravitational acceleration as well as the true acceleration. In this case, accelerometer input axis tilted downward result, as well as the true acceleration. Accelerometer input axis tilted downward result in a negative gravitational acceleration component being measured as the accelerometer proof mass tends to move in the same direction as when the vehicle is being retarded. So we have negative acceleration. Next picture, t equal from 0 to 21 minutes. As the aircraft flies over the Earth, the negative acceleration error resulting from the platform tilt is integrated with time and causes the computed vehicle rate to become slower than the true vehicle rate. The platform is thus being rotated at a progressively slowed rate than the local vertical, thereby reducing the tilt error. At time equals 22 minutes to 42 minutes, the accelerometer error due to the platform tilt is now positive. So that the platform, so you can see in here, so that the platform rate of rotation starts to increase. After that, from time period at the 42 minutes, the platform is now rotating at the same rate as the local vertical. Next period, from time before 42 minutes up to 63 minutes. After 42 minutes, the platform vertical is now starting to rotate at a faster rate than the true vertical. By 63 minutes, the platform tilt is 0 again, right? However, the platform is now being rotated at a faster rate than the local vertical. And next period time, to 63 up to 84 minutes, the tilt has changed sign so that the platform rate of rotation now starts to slow down until it gets 84 minutes, and it's rotating at the same rate as the local vertical. So the whole cycle is repeated over the next 84 minutes and so on. Next time we will be continuing our lecture according to inertial navigation. And for this moment, I think you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.